Hey everyone, welcome back to environmental restoration. I hope you all are doing well. Missed you all. It's been a crazy transition for all of us, and I hope that we're able to adjust to this remote course delivery for the rest of the semester that you've all been rolling with in your other classes too. So this is me in my new classroom here with my headset on, recording my PowerPoint lectures. This is the first time I've ever done this, so it's going to be a pretty major learning experience. So please be patient with me. I'm going to learn a lot as I go and provide lots of feedback, which would be great. I hope you've seen the emails that I've been sending out. Those give details on how our class is going to work. We have our Google Hangouts once a week, which are not mandatory, but of course you're welcome to check in just to say hi, see how things are going, and feel free to drop me a line if you want to be in contact some other way, by phone, Google Hangouts at other times, whatever works for you. And we can just all be patient and flexible with each other and adjust to the new normal. So welcome everyone. Sorry this PowerPoint went up and video went up a little bit later than I planned. There were some technical difficulties, probably not for the last time. So we're talking about stream restoration, and we began by mentioning the negative impacts of human activities on streams, these 7 different sort of categories, and then thinking about how our stream restoration activities are trying to address those. And today I wanted to talk a little bit more about how restoration works. So back before spring break and all this craziness happened, we talked about this natural channel design process. And some scientists that had evaluated it and tried to think about how well it worked. This paper concluded that it doesn't work very well. Similar to this paper. And so this Roskin classification, or natural channel design as it's referred to, is really the approach that is generally taken for compensatory mitigation. So it's a bit concerning that geomorphologists that have studied it have concluded that it doesn't really work all that well. Okay, but what do the ecologists say, right? Or maybe more accurately, what do the species say, right? How are they responding to these sorts of things? It's just a study done in eastern New York State in the Catskills. Actually had a student who had a job out there this past summer. And so they looked at all these different streams, and they did what's called a Abaki study design, before-after control impact, where they collected data before restoration and then after restoration to see how, in this case, the fish populations responded. So here's a table of their data. The highlighted column there is the p-value, looking for differences in the fish assemblages after restoration. And those bold values, again, are statistically significant at a cutoff of 0.05. And the mean response column, 2 columns over to the left, is the post-restoration value minus the pre-restoration value. So a positive value indicates an increase due to restoration. And you can look that over. So the total number of species increased by about 1.5 after restoration. Total biomass increased by about 3 grams per square meter after restoration. And you'll notice this trend was particularly strong in that grouping below there with salmonids, so trouts, brown trout in particular. So it looks like in these particular instances in these streams, there was an increase, particularly in trout, after restoration. The authors argue that this was due to a response in increased quality and quantity of habitat for these species, as well as increased substrate particle size post-restoration. They also showed a slight shift from tolerant species, those that are able to hang out in the presence of habitat degradation, and then shifting toward intolerant species, those that aren't able to survive when degradation is going on. And when we think about what natural channel design does, in particular these in-stream structures like this cross vein, we might expect that it would be beneficial to larger fishes, right? With this cross vein, we're bringing in big boulders, we're creating pools. Those are the kind of habitats that if you're a trout fisherman, you love to go and fish. So when we bring in these kinds of habitats, it does appear to have a positive impact, at least on some fishes. But what about the invertebrates? Well, this was a study that analyzed the data from this very same study, but looked at invertebrates rather than fishes. And as you can probably conclude from the title there, they argued that these natural channel design restorations really didn't do much of anything for the macroinvertebrates. As we've discussed, watershed scale factors are really the things that drive degradation of streams, and invertebrates are the ones that are going to be affected the most by sediment deposition, those kinds of things. So it looks like the macroinvertebrates were not responding in the same way that the fishes were. If you go back to the results of my research students and I, when we were in the Ivy River watershed up in Madison County, we found something similar. Looking at the p-values there on the upper part of that panel on the left, there was a marginally significant increase in about a little over 2 species on average, 2 more species of fish in the restored than unrestored sites. Whereas the invertebrate-based metrics there, percent EPT and an index of biotic integrity, really no difference. Over there on the right, you also see that we found, interestingly enough, fewer fish in the restored sites. And that was largely driven by the large numbers of tolerant fishes that were hanging out in those unrestored degraded sites. To look at another local example, this is Cane Creek down in Fletcher. And so it went from this incised channel full of invasive multiflora rose, not much water moving at all, to this later on in that same year. So they reconstructed the channel, moved it out of that riparian forest, which you can see in the background there. And right after it was built, there was no vegetation. They'd created a new channel, recontoured it. They'd done plantings on the banks, but nothing had really grown in yet. So this is what it looked like. Now in 2016, it looked a little bit like this. And so this is in year 4 of the restoration. And so, of course, you don't have any trees or anything established there, but we're getting a little bit of vegetation that is starting to resemble perhaps a natural stream bank in some ways, and at the very least is providing root biomass and things to hold those banks together and reduce sediment input. So we sampled the invertebrates. The stream really wasn't big enough to support many fish, but looking at the invertebrates, we went from 1% EPT pre-restoration, and when we went back in there post-restoration in 2012, there was really nothing living there. So no, again, right, mayflies, stoneflies, caddisflies. When we went back in 2017, interestingly enough, it was up over 40% EPT. So this is a really interesting site that I would like to go back to again, because there appears to be some evidence of improving habitat quality a couple years post-restoration. Now, this could possibly be simply because the condition was so bad initially, but nonetheless it's interesting. And I'd also point out that 40% EPT is habitat quality comparable to what we would see at Glens Creek at UNCA. So this isn't turning into a pristine stream at all, but it's interesting. There might be one case here at least where there's a bit of improvement. So if we go back to the list of stressors and think of what we've been attempting to address so far with the natural channel design, So number 2, morphological modification of channel and riparian zone. Certainly that's what natural channel design is attempting to remedy. Excessive erosion and sedimentation, that's the watershed-wide impacts, which are so difficult to deal with in general. But some riparian plantings and that kind of thing can at least attempt to remediate that. Deterioration of substrate quality, you can fix that to a certain extent just by bringing in larger rocks when you're doing natural channel design. And of course, when you keep the sediment out, then you're improving substrate quality. Deterioration of water quality, again, that's that watershed-wide issue, which is so challenging to deal with. Decline of native species, of course, the native species are an emergent property of the ecosystem, and they're going to respond to habitat degradation. So everything that's listed above is going to lead to a decline in native species. And then introduction of alien species is really not a big issue where we are, but in some places, particularly out west, it can be a concern. And so if you remember our earlier discussion of active versus passive restoration techniques, we discussed a non-native parasite which affects trout, and when the restoration provided shade to the stream banks, it created conditions that weren't ideal for that alien species. So to some extent, we've attempted to address that. But the one at the top, water quality or flow mistiming, anything we do within the channel itself as far as reconstructing it, recontouring it, is really not going to address that. So the question is, why is that a problem? How did that come to be? And it's due to dams. It's due to impoundment. So this is an image off the National Inventory of Dams that's maintained by the U.S. Army Corps of Engineers. This figure always blows my mind. So over 70,000 catalog dams. The total is estimated to be a lot more than that. But the other interesting thing when you look at this is that color coding of the dam height there on the lower right. And so you look at all the green there. So those are relatively small dams, 0 to 25 feet. You see those larger red ones, the Tennessee Valley Association dams there, up to the north of us, out west, right? More dams. But the majority of them are these small dams. Sorry, I think I got cut off there. The majority of them are these small dams. All right, well, here's a little diversion I thought I might share with you. This is a project I got involved with when I was in Nepal in 2015, 2016. We built most of our dams in the U.S. Post-World War II, or even during World War II, to create hydropower that was involved with industry, and also some were created for recreational use. But Nepal hasn't built many dams yet, and there's incredible hydroelectric potential there, but some negative impacts on the ecosystem. So we were interested in seeing what potential effects construction of dams on Nepal's Karnali River might have. So Google Earth image of the river in red, and all these planned hydroelectric dams are those little orange triangles. There's a bunch of them. You see the one that says Upper Karnali Proposed Dam Site. That's the site on the river that we were trying to evaluate, kind of above and below it. Getting around is tricky in this part of the world. This is our Jeep driving along these roads very carefully. I try not to look out the window. You can just see the back of that van too. It's kind of cool. It's got this, or that Jeep. It says free Wi-Fi on the back, but there was no free Wi-Fi. It was purely decorative. This is kind of a sad picture. This is survey work done for where that dam's going to be constructed. And you can see in the upper center a pilot hole that's been dug there. That's how high the water level would be once the dam was constructed. And the water would rush through that hole and actually, interestingly enough, down through that mountain, downstream into the river. So they wouldn't even have to build a very big dam. This is our crew. The the guy there to my right, actually I wrote a letter of recommendation for him, just got into Yale School of Forestry, so he's going to be going there soon, assuming that situations get back to normal in the near future. So I might show you just a couple of fish that we found. This is, the rivers out there. You see this wide floodplain with no vegetation on it, and that tells you this is a river that floods pretty high during the monsoon, right? Because that keeps vegetation from really getting established. So we came in here and sampled. And found some cool stuff. These little puffer fish, this one on the upper left, they were living in this vegetation, and we're like, wow, what are those? Oh, they're puffer fish. You'd hold them in your hand, they'd puff up. And this crazy shrimp that I'm holding right there with these huge claws. They were crazy looking organisms out there. So when you go up a little higher into the river, you get into these rapids. These are a couple students from Kathmandu University that came with us to do the work using an electrofisher. They did an awesome job, and they have really cool hats. And some of the fish we catch here are adapted to live in high flow velocity habitats. So the catfish on the bottom has those grooves on its ventral surface, which it uses as a suction cup to latch onto rocks. And then the fish just above that also has a suction cup below its jaw that it uses to attach to rocks. So you kind of see the morphological adaptations of the fish to live in this part of the river. Clearly, this kind of habitat, this kind of rapid habitat would go away if you created a dam. Here's me looking really cool in this bridge overlooking a village. And this is kind of sad because when this dam is built, if it is, this village would be underwater, so everybody would have to move. Fishing is a big part of the economy in these areas, so these folks are getting ready to float a net out into the river to catch fish. But if this dam does go in, nobody knows how it's going to affect aquatic biodiversity. So these fishes, the one on the top is the genus Schizothorax. It's called a snow trout, although it doesn't live in the snow and it's not a trout, it's a minnow. The one on the bottom is called Masir. It's actually an important sport fish. But we have no idea how these fish are going to be affected if that dam goes in, because people haven't studied their migration patterns at all. This is us hanging out. This is our team. We would stop by these shops in the marketplace for a cup of chai. You can see in the foreground there, and just kind of hang out. I'm rocking my UNC Asheville shirt right there. This is one of our sites there. The other Jeep got stuck, so our big Jeep had to pull it out of the sand. Of course, I'm standing back watching, taking pictures. Yeah, so then there was this expedition that was put together called the Save the Karnali Expedition, and I was involved in writing the grant to get money for this project. Unfortunately, though, it got delayed to the fall, and so I wasn't able to go. But the idea was to bring awareness to this river so that it wouldn't be dammed, because it is free flowing. This is the team. I'm not on it. I'm not bitter though. No, not at all. This is everyone there. They did a lot of kayaking. In fact, there was an amazing first ascent in the headwaters. It started up in Tibet and then worked its way down. It was pretty amazing. Facebook posting where they actually saw a freshwater dolphin near the Chisapani Bridge. If you can see in the background the bridge on the upper photo, that's the bridge where there was a picture of us that I had on the first slide. So yeah, freshwater Gangetic dolphins are actually found in this river. It's pretty crazy. All right, so back to the U.S. So with dams, if they're used for hydropower, they're regulated by the Federal Energy Relicensing Commission. And there's a 30 to 50 year licensing period for non-federal projects, so like private hydropower dams. So when that permit comes up, dams have to be brought into alignment with current regulations, which of course are more stringent now than they were 50 years ago. And as part of that process, the Fish and Wildlife Service makes recommendations to FERC concerning fish and wildlife. And so if there are migratory species in the river, for instance, they often recommend something to improve the ability of fishes to move past those dams. So about 2/3 of all relicensing processes require fish passage modifications. So those can be things like fish ladders, which let fish get around the dam. But sometimes, especially if they're not generating much power anymore, it's actually cheaper to simply remove the dams. So this is an approach to stream restoration that addresses the flow issue. This is a dam that was taken out on the North Toe River between Spruce Pine and Burnsville, for those of y'all that know the area up in Mitchell County. So let's look at a couple case studies to see how this improves streams. So this was a project with a couple dams that were removed in Wisconsin back in the 90s. And you can see these aren't huge dams. You can see from the back. It's a pretty dramatic process. You kind of take these dams out in chunks, and you know, a lot of sediment moving downstream, a lot of heavy equipment involved in this kind of a project. So these authors looked at what happened to habitat quality when these dams are removed. And so on the x-axis there, you see we're going from June 96 to November 2000. And there's a biotic index on the y-axis. And the higher numbers are poor, lower numbers are good, right? So each of these symbols represents a different site. And I just want to point out that site D, the inverted white triangle, was impounded behind dam number 2 and behind dam number 1. I feel like it's a game show. Was site B. But both of those were in poor condition, and that poor condition comes from the invertebrate communities. So if you're wondering what kind of invertebrates are given poor classification, this is done on a family level, not an order level, like our percent EPT. And so midge larvae, cranefly larvae, which you guys may have seen in 241 if you sampled streams and looked at inverts, those have poor classifications. Oligochaetes, nematodes, flatworms, things like that. So then dam number 2 was removed before April 98, dam number 1 before April of 2000. And when you look at both sites D and B, after the dams were removed, the habitat quality got a lot better. So you look for those white inverted triangles in April 99, they're down around the good to fair quality, right? And even good, right, in 2000 there. Again, you look at site B and you see some open circles. They're overlapping there, but they're in those, again, they've moved out of the fairly poor area. So it does look like, based on these data, removing dams does a pretty good job of improving habitat in the area that had been previously impounded behind the dam. So in addition to dams restricting movement of species, they also degrade habitats. This is a picture of what the stream banks look like a week after removal of that dam, and you can see it's all mud and silt, right? So this is not high quality habitat behind the dam. So when you take that dam out, the water comes through, washes that silt out, and it creates better habitat. We were involved in a study on the North Toe River looking at that spruce pine dam removal. And I'll just share here, you know, we didn't find a big change in habitat quality upstream of the dam after it was removed. And there's a couple of reasons for that. I think the first is that the dam was partially breached already. It was damaged during a flood. And the other thing is that this is a mountain stream. So there was not a big reservoir behind it. There was not a big sediment-filled pool. So, you know, I just think our study sort of showed that responses to dam removal may vary based on the ecosystem where you are. But clearly, if you have migratory species involved, there are going to be benefits. And this is an American eel. Interestingly enough, there are species in the same genus that live in rivers of Nepal. But the American eel can live to be 30, 40 years and older, and they live almost all their adult lives in freshwater. They can live for up to 25 years in freshwater rivers. Then they migrate out into the Atlantic Ocean to the Sargasso Sea to spawn. And then once they mature, they move back into the rivers. But these things migrate way up the rivers. They found them as far inland as Oklahoma. But of course, to be able to migrate, they have to be able to get around dams. So this is a paper that found that removing dams has increased the ability of American eel to get back into these streams, which are in some cases over 500 miles distant from the Atlantic. So removing dams definitely increases abundance and aids any kind of migratory species. So this is a colleague of mine at App State who asked the question, are there trade-offs associated with removing these dams? When you think about it, these are pretty dramatic operations, right? You're in some cases blowing up a big cement structure in the river, and we don't know that much about it. It's been pretty new. So this is the point in the lecture where I'd ask you all to think what the negative aspects of dam removal might be for an ecosystem. So Mike Gangloff, he studies freshwater mussels primarily, so thinking like a freshwater mussel, what might be the issues here? They're filter feeders, they live on the bottom of the stream, they have to kind of burrow into the substrate to be able to live. So he mentions a couple things. First of all, he just points out that we don't know a lot about the impacts of these smaller dams, and that they may not be as great as the impacts of these larger dams. So maybe there's not as much of an upside potentially to removing these small dams. He points out that freshwater mussels often do very well immediately downstream from dams. So if you think of what a dam does, it's trapping sediment, right? And so when the sediment flows over that dam, when the water flows over that dam, it leaves a lot of the sediment behind. So you've got pretty clean substrate downstream from these dams often, and so it's a place that freshwater mussels often seem to do fairly well. So if you remove a dam, you might lose that. So there's some cases where native species live in the headwaters of streams and they're protected from negative impacts of other species by these dams. Here in the southern Appalachians, the only native trout that we have here east of the Rockies is the brook trout, and in particular we have a strain called the southern brook trout that lives here that's genetically distinct from brook trout in other places, even in the east. So in the early 20th century, when brook trout were stocked all through the U.S., to be honest, they brought trout in from Pennsylvania, and so those trout interbred with our southern strain brook trout, and that was problematic, except for places where there were barriers to migration, so that these trout were stocked but weren't able to migrate up to breed with brook trout. There are also cases, there's a species called the sea lamprey, which is a terrifying fish if you want to Google that. And it's an ectoparasite on large-bodied fishes, and they need to get into rivers and streams to spawn. They colonize the Great Lakes. And so small dams can keep those invasive species from getting upstream. So Mike is making the case that in some cases these small dams might actually restrict movement of invasive species where they occur. Or in the case of our southern strain of brook trout, those dams might be sheltering some headwater populations from interbreeding with the other type of brook trout. He argues that, the way our streams used to be, there were a lot more beaver dams, a lot more log jams, and so arguing that maybe these dams create a little more natural type of habitat than we would normally see without them. I'm not sure what I think about that. And the final point he makes just is that anytime you remove a dam, you release those large amounts of sediment downstream. And if we remember that these dams were all built, well, a lot of them were built before the Clean Water Act, there was all kinds of stuff going into our rivers. And so there's toxins, right? We use DDT as a pesticide, all kinds of things that could potentially be associated with this sediment. So when that's released and goes downstream, that could be a problem. The dam removal we were involved with on the North Toe River, they had to take a core sample of the sediment and test it for contaminants, and it was clean, so they went ahead and took that dam out. But it's something to think about. All right, so backing up here again, how effective has stream restoration been as a whole? This is an article that Margaret Palmer and authors wrote on the Annual Review of Ecology, Evolution, Systematics. And so, just once again, they concluded that in many cases, water quality is really the limiting factor to establishing a natural biological community. And so until you have higher quality water, improving the in-stream habitat may offer few benefits. Although, as we mentioned earlier, with larger bodied fishes, the habitat can sometimes benefit them. But for other fishes and invertebrates, few benefits. And then they conclude with this thought, which is that river restoration so far is a pretty new science, newer than forest or prairie restoration. You know, although Leopold was involved in prairie and forest restoration back in the early 20th century, rivers and streams and wetlands to a certain extent too, we've really only started trying to restore since the Clean Water Act charged states essentially with trying to improve the quality of their surface waters. So we're still learning a lot about it. Again, and then they state there, right? Unfortunately, this major emphasis seems to be on recontouring stream channels, these structural interventions, as they say, despite growing scientific evidence that these approaches do not work particularly well. So again, they highlight the importance of working on the watershed and riparian scales to improve the quality of the water that's coming into the streams to begin with. Again, the most prevalent water pollutant, sediment, right? If we can keep that out, then our streams as a whole are going to do a lot better. So this larger scale perspective is really what's needed, and we've learned that in the last 30 or so years that there's been a lot of research going on with stream restoration. The final thought I'd say is just how interesting it is. I mentioned in the beginning of class how cool environmental restoration is. Number one, because we're doing it to try to learn about how to improve our ecosystems. Number two, because these are sort of like large experiments where we really determine what is causing degradation of our ecosystems, right? So this work on rivers and streams has shown us that, look, it's not the stream bed itself that is causing this degraded water quality. It's factors at the watershed scale. It's factors in the riparian zone. So we've learned a lot about how rivers and streams work, what degrades and stresses them from our practice and our learning about stream restoration. But as Palmer et al. Point out, and the thinking on this, I'll tell you, has not changed since 2014, we really need to think on the larger scale. So I hope y'all are doing well. Again, let me know if you have any questions or comments on how this whole remote learning process is going in general, and anything on this lecture in particular. Feel free to leave comments on my YouTube channel. I think I have set it up to be able to do that. But even beyond that, feel free to drop me a line or connect with our Google Hangout time as well. So I hope y'all are well. Just think about this time, man. I hope you guys are keeping journals, right? If you're journaling, because this experience, right, with COVID-19, you're going to remember it for your whole life. So just write down kind of what you're learning about yourself and thoughts you have on society and all sorts of things. It's really pointing out how we're all connected to one another. And I think there's some important lessons there for ourselves as a global species that we're learning through all of this. So hope y'all are well, and I look forward to connecting with y'all again soon. Bye now.